We have completed a year-end technical stop of Atlas, of the Atlas experiment. This time it was a rather short stop of only essentially 3 months. We did not have to do too many repair work, normal maintenance work, and so we are looking forward now to the exciting data taking period which starts now.
So 2018 is our last year of data taking before we shut down for several years. So it's a really exciting time and we need to make the most of that data. So we're going to be spending, our primary focus is still on understanding the Higgs boson. So as you know, we recently discovered the Higgs boson, but there's a lot about it we need to study. So we're going to be taking as much data as possible in order to understand that. And we're also going to be looking for physics in places that we haven't seen it before.
So in 2018, so we are going to take another set of large amount of data, like 70 inverse femtobarn, which corresponding to 40% greater than the last year. And it maybe this number is still standing on the safe side, and we hope that we get more than that. In any case, so it's quite a large amount of data, and it will be a very exciting and important year in 2018. And something special with respect to the last year is for every collision, like so lower pileup of events than last year. So it is also good for the precise physics analysis. So last year we need to run with under very high pileup condition. However, this year with putting many larger number of bunches in the machine, and on the other hand, the number of pileup events becomes less than the last year. So the situation is quite preferable on our side, I mean the detector side. So I'm pretty sure that we are able to take data in a better condition than the last year.
So I think one of the really fun parts about what's going to happen in 2018 is that we're going to have, since when we turned on at 13 TeV, the focus was on exploiting this additional energy that we have and looking for things that were very heavy or very massive. And so we are kind of reaching a point where that's not the most exciting thing anymore. The most exciting thing now is to look for extremely rare things or things that we're just not sensitive to anymore. So there's a lot of different types of new physics out there that our normal algorithms and our normal detection techniques are not sensitive to. So we have to go back and we have to redesign our algorithms, redesign our search strategies such that we can find very rare things. So we can find particles that might be dark matter candidates or connected to what dark matter is that will travel in the detector and decay somewhere. So the standard model is a very rich and complex theory. What we need to do is measure all of those interactions at this very high energy that we haven't done before. So many of our standard model measurements, precision measurements of cross-sections of particles that we already know exist, can tell us a lot about the structure of the standard model, and we have not yet made those measurements. And so a big focus will also be on really making these beautiful, precise measurements of the standard model so that we can understand this fundamental part of particle physics.
So since we collected such a large data set, it has a lot of potential, so please stay tuned. We will, of course, do the easy part first to look for easy signatures, but then it will take some time to address more complex scenarii and also to do precision measurements and control the systematic uncertainties very well.